So for this video, we'll mostly be working on forces, sum of forces, free body diagrams, and then we'll finish with example problem number 6. So first, what we're going to work on is free body diagrams. It's pretty much just a good visual way to know where all the forces are, and so you don't forget anything, and so you have a representation you can just look at. So let's just start simple. Let's say we have a box with mass 1, okay? If it's by itself, if it's just by itself, it's going to have this force here, mg, while if it's on a table, it's still going to have that force, that mg force, but then it's also going to have a normal force because because it's not moving, and any force like the force that the box exerts on the table exerts back onto the box, right? So theoretically, we could break this down even more and say, oh, the table legs are exerting a force on the ground, and the ground is exerting a force back onto the table legs. The table legs. But we'll just focus on this right now. Next, we can do a very common example, a box on a slope. So we'll have this be m again, m1. So of course there's this force, mg. Then there's the normal force, and that can be broken up into components. We'll do that in a second. And if there's a component going up the slope would only be if there's friction. So if there was friction, we would say F. But if there's no friction, friction is negligible, then there's not going to be anything there. So for this, we can break this up into, say we have angle theta here. We can break this normal force into two forces, so it's like this. We can break it up into two forces here and here, but we'll worry about that later. I'll show you in the example problem. So the example problem is a block of mass m1 is connected by a string to a sphere of mass m2. The block is a frictionless plane inclined at an angle of 30 degrees. As shown in the figure above, the string passes over a pulley of negligible mass and friction, and the sphere hangs freely. Which of the following is always true if the block is accelerating down the incline? So we can draw this. We'll draw this m2, m1, and one key thing to note here is that it says frictionless, so there's not going to be a force of friction going up the slope. So we can already do our free body diagram. mg right here, m2, or actually that's m2g. This right here is m1g, and we have the normal force upwards, normal. So that can be broken up into we can break this up into m M1 sine 30. M1G sine 30. So that's the force that's going to be moving towards the right, because these forces, the normal force, breaking the normal force down, we'll get the way in which it's moving, we'll get or big M1G sine 30. And we know that M1 block is moving this way. So now we know that this force has to be bigger than this force. So we can M1G sine theta is greater than just M1G, and then we can cancel that out, cancel the G's out. So what we'll have left with is M1 sine 30 is greater than M2. Yeah, sorry, this is supposed to be an M2 as well. So that's our answer. And now, as you can see, that's option E, and that's the correct answer.